In this session, we are going to discuss the breadth first search algorithm. So, in our last session, we had started discussing the graph traversal algorithms, and we looked at depth first search. And, and in this session, we are going to mainly focus on the second graph traversal technique called the breadth first search. So the idea here is that given a graph, how can we traverse through this graph using a more standardized approach? So a breadth first search uses a queue data structure, whereas a depth first search, if you recall, was using a stack as the main data structure. So here we are using a queue. It may be worth recalling that a queue would always follow a first in, first out principle, right? So whatever the first node or the first element in that queue would be the first one to be sent out, right? So let's say that we are given with this graph, and we start with the node with the value 0, and we would like to visit all the vertices in this graph using the BFS approach. So first thing first is we would need to maintain a queue, and we would also need to maintain a result array to show our final result. So we start with 0 as we did in the DFS, and then we are going to add that to the queue. As you can see here, we are adding it to the queue, the node that we had visited. And then as a next step, we are going to dequeue that node, make it visited, right? Make it visited and dequeue that node. And then at that point, we are going to look at all its neighbors, which are 1 and 3, and we are going to enqueue them into this queue, meaning we are adding it to the queue, and we had dequeued 0. Every time we dequeue an element that has been visited, we add that to the result array, right? So now you could clearly see that 0 is added to the result array, 1 and 3 are enqueued to that queue. So the next step is going to dequeue the element in the queue, which is 1, and then we look at all its neighbors, 3, 2, 6, and 5. So there's no particular order in which the neighbors could be explored, right? So we could follow any order according to the principle of BFS, but here we are just going to queue them like 2, 5, and 6. I'm not enqueuing 3 because it's already present in the queue. You can see that, right? If a node is already present in the queue, then we don't enqueue that again. So as to make sure there's no repetition, right? So 2, 5, and 6 are all enqueued, and 1 now is visited, and then it's added to the result array, right? And you could also see that a dotted line is added here, so as to make sure that from 0 we had visited 1, right? And at any point of time, you know that where did we come from to 1, right? So we came from 0. So this is why 0 and 1 is a dotted edge. So we know that we visited 0 first, and then we came to 1. So the next thing in the sequence would be 3. So we dequeue 3, and we make that as a visited node, and we add that in the resulted array. And now you could see from 0 we came to 3. This is why there is a dotted edge between 0 and 3, right? So we came from 0 to 1, and then we are going from 0 to 3 according to this particular graph so far, right? And the next element in the sequence would be 2, which is dequeued, and we are adding it to the result array. And then you could see the list of neighbors for 2. So we have 2's neighbor 5, 4, 3, and 1. And then you can clearly see that 1 is already visited, and 3 is also visited, and then 5 is already in the queue, right? So 5 was already in the queue, and so all we need to do is we are adding 4, right? So we add that 4, and you could see that at this point we don't need to add any more edges, right, or neighbors I should say, because including 4, all the nodes are already present either in the queue or that's something that we had already visited, right? So we just leave that alone at this point, and then we dequeue 2, and then we go to 5, the next element dequeued. 5 here is also, you can see that there's a neighbor 1, 2, right? And 1 and 2 is already visited. So there's two things that we should check. One is it visited? Second thing is it already in the queue? Right? If the answer to both those are no, right? Then, for example, let's say it's not visited, it is not already in the queue, then we should be able to add that to our queue. Otherwise, we don't add it to the queue, right? So for 5, we find that the neighbor or 1 and 2, 1 and 2 are both visited already, right? So we don't need to add any neighbor to the queue again. So the next thing would be 6. Clearly you could see for 6 the neighbor or 4 and 1, and then you could see 1 is already visited, 4 is in the queue, right? So we don't need to add 4 again. So we simply leave that alone, and then we are going to go to the next node in that sequence, right, which is 4. And you can clearly see 4 at this point would have the neighbor 2, 6, and 3, right? All of them are 3 is already visited, 6 is already visited, 4 is already visited, right? And I should say 2 is already visited as well. Let me get rid of this 4 here. So you could see clearly that all the neighbor are visited. So we could dequeue that, right? But keep in mind, now that we are visiting 4, we are adding a dotted edge between 3 and 4. Why? Because we are visiting 4 basically from 3, right? So again, a quick recap. Let me go back to the next slide. Now the queue is empty. So we had added all the nodes that are visited. A quick recap here is 0 to 1 was the first edge that we had made visited, right? We had explored. And then we came from 0 to, at that point, 3. And this is breadth first, right? It is going broader and broader into the graph. And then we picked up 1. So we visited 1 to 2. And then we visited 1 to 5. And we visited 1 to 6. Right? So we had, at that point, we had visited all the neighbors of 1, which are unvisited. And then at that point, we go back to 3. You see, from 0 to 1, then we picked 1, and then we had visited all the neighbors of 1. Now we're going to pick up 3, and from 3, we had visited 3 to 4. So that's the idea here, is that at any point of time, we are going broader and broader in the graph. So in BFS, we are going broader, and in DFS, we are going deeper into the graph. Okay. All right. Well, let's look at this algorithm here. How can one implement this BFS procedure? So basically we need to have a queue, and then we are going to enqueue the first element u, which is coming in, the first vertex. And then we check if queue is not empty, we dequeue the element, and we check if visited of vertex s is equal to false. That's the check that we do initially. If it is false, then we are adding it to the result array. And then we also make that visited of vertex s is equal to true, so that it is colored as that red node there in our graph. Basically, we are saying that we had visited that vertex. And then we are going to look at all m element of the neighbors of s. If visited of vertex m is double equal to false, then we are enqueuing it, right? So we enqueue that neighbor to that queue, as we did in our example. So we do that for all the neighbors. So this is why there is a for loop here, unlike DFS. It's what recalling that in DFS we were only adding one neighbor, and in BFS we are adding all neighbors. That's the main difference, right? Okay. So in terms of the time complexity here, again, you could see that in the queue, the maximum number of nodes that will be added in the queue will be capital V, because that's how many vertices that you have in your graph. And then for each vertex, you could see that if you have a graph like this, then for each of those vertex, we are going to go and explore its neighbors, right? We go and explore its neighbor. And when we explore these neighbors, the total number of neighbors is simply going to be the total number of edges, right? So which is capital E, that's the total number of edges. So thereby, the time complexity is going to be big O of capital V plus E, similar to what we did for DFS, right? Again, the logic is still the same, because the total number of neighbors that we are exploring is simply going to be the capital E, right, which is the number of edges. And then total number of nodes that we are exploring is capital V. We simply need to add them, and it's still linear, as we talked about last time, because it's going to be big O of n if we assume that the number of vertices and edges, or n, is going to be big O of n, and thereby it's linear. Okay. So we will take up a tryout exercise here to practice BFS. Earlier in the last session, we had practiced DFS on the same graph. So this is our opportunity here to practice BFS. So let's say we start with the vertex A. So I like to see in your solution that you include a queue and a result, like what we did in our example. And please make sure to post your solution in our general channel. And if there are any questions, you should feel free to ask while you're solving this problem here. The next step for us is that we would look at Dijkstra's algorithm, which is the shortest path algorithm in a graph. And then in a graph, we will also look at minimum spanning tree algorithm. So we will look at the Prim's algorithm and Kruskal's algorithm next week. And at that point, we should be able to complete the graph data structure algorithms. And if time permits, from there, we are going to look at string algorithms as the next step, right? So towards the end of this session, end of the semester here, we are going to look at a few string algorithms as well. And there is a reading assignment. If you have not done so already, I recommend that you go back to our Sedgwick textbook and do the reading assignment 4.1 and 4.2. And then if you have any questions in this process, as I said, you could again contact me through Slack, email, or during the virtual office hours. And I'm also going to follow up on the lab in my announcement. So please look at my announcement for the related to the lab session today. Okay, so thanks for watching this video.